Hello, everyone. Welcome back to our online version of Math 262. This week my handwriting should be better than last week because I'm using a better app. So I apologize for last week's handwriting. Hopefully this week is an improvement. So I want to give you a quick reminder, WebAssign is due Friday, and make sure that you turn in a copy of your notes each day. It's a little bit onerous, but I do that so that I can give you credit for watching the videos and so that I know that you're engaging with the material. All right, so let's begin. So we've learned about a lot of different tests to see whether a series converges or diverges. And today we're going to learn about a new one called the ratio test. So the ratio test is another way of determining whether a series is convergent or divergent. So we're going to have a series, sum of a sub n, and we're going to assume that the terms are non-zero. So the terms are not zero. And we have the following criteria. We need to take some limits. So if the limit as n goes to infinity of the absolute value of the an plus 1 term over the an term is a limit less than 1, this tells us that our series converges absolutely. Converges absolutely. And if the same limit is bigger than 1, this tells us that our series diverges. Lastly, if our limit in question is actually equal to 1, unfortunately, in this case, it tells us nothing. All right, so the ratio test is essentially a way of estimating, is this series something like a geometric series or is it not? And we know that a geometric series should converge when the ratio is less than 1. Just like here, we converge if our limit is less than 1. It should diverge if our limit is bigger than 1. That's what happens in case 2 here. So this one, it diverges. And in the last case, if our limit is equal to 1, then, it equals 1, then the ratio test is inconclusive. Okay, so for the ratio test, we want our limit to be less than 1 or bigger than 1 because these are the situations where we get a conclusion about our series. So let's do some examples, and I think you'll find out pretty quickly that the ratio test is everyone's favorite. So let's look at an example here. And our first example will look at the series n over 2 to the n. So that's my an term. And this tells me that an plus 1 is n plus 1 over 2 to the n plus 1. So if we take a limit of n plus 1 over 2 to the n plus 1, and the denominator we have n over 2 to the n, this will equal a limit as n goes to infinity of n plus 1 over 2 to the n plus 1 times 2 to the n over n. So now we need to simplify this a little bit, and we see that these terms are going to cancel, but there'll still be a factor of 2 left in that first denominator. So now we're taking a limit as n goes to infinity of n plus 1 over 2n. And I think we all know that limit is 1/2 because the numerator is a degree 1 polynomial and the denominator is a degree 1 polynomial. So the limit is the ratio of their leading terms. And that in particular is less than 1, which tells us that our series converges absolutely. All right. So let's do an example where it's going to diverge. So let's do the example where we have the sum from n equals 1 to infinity of n factorial over 2 to the n. Okay, so that's an, and therefore an plus 1 is n plus 1 factorial over 2 to the n plus 1. So in order to use the ratio test, we take the limit of n plus 1 factorial over 2 to the n plus 1 all over n factorial over 2 to the n. So that's a little messy, but let me write it in a way that is a little more clear. We have n plus 1 factorial over 2 to the n plus 1 times 2 to the n over n factorial. All right, so we see we get a similar cancellation as before, but the question is, how do n plus 1 and n factorial interact? Well, we know that n plus 1 factorial is 1 times 2 times 3 times all the way up to n plus 1. And n factorial is 1 times 2 times 3 times all the way up to n. So if I'm dividing them, I see that everything is going to cancel out except for the n plus 1. So what that tells me is that these will cancel out, and I'll be left with an n plus 1. Therefore, this limit is the limit as n goes to infinity of n plus 1 over 2, which equals infinity, and that's clearly bigger than 1. So the conclusion from all of this is that the series, it diverges by the ratio test. All right, so we've seen an example now where a series converges and a series diverges by the ratio test. And now I think it's time to look at some examples where the ratio test actually tells you nothing. So let's look at this example. This is the harmonic series, and that's our an term, which means our an plus 1 term is 1 over n plus 1. And so we need to take a limit in order to use the ratio test. So we do the limit as n goes to infinity of 1 over n plus 1 over 1 over n. And if I do the algebra, what I see this becomes is 1 over n plus 1 times n over 1, which is the limit as n goes to infinity of n over n plus 1, which is 1. And so what this tells us is the ratio test is inconclusive. We actually know this series diverges, but the ratio test could not tell us that. All right, let's do another similar example. Except this time we're going to look at 1 over n squared. This is our an term. And an plus 1 is 1 over n plus 1 squared. So, like all of these examples with the ratio test, we take a limit as n goes to infinity of 1 over n plus 1 squared over 1 over n squared. And I'll skip a little of the algebra this time. We get n squared over n plus 1 squared, which is the same as the limit as n goes to infinity of, well, let me put that onto the line. N squared over n squared plus 2n plus 1. So we know that this limit is 1 because the numerator is a degree 2 polynomial and the denominator is a degree 2 polynomial. So the limit is the ratio of leading terms. And therefore, what this tells us is the ratio test is inconclusive here. So we know this series actually converges because it's a p-series with p equals 2, but the ratio test isn't strong enough to tell us that. So the general rule of thumb, the rule of thumb here is that we use the ratio test. We typically use the ratio test. When we have expressions. Involving things like n factorial or exponential functions. Such as 2 to the n or e to the n. These are times where we use the ratio test to find out where the limit converges or diverges. All right, so now it's your turn to work a couple examples. And I'll give you a few minutes to do it, and then I'll tell you whether they converge or diverge. So some examples. I want you to use the ratio tests to pause the computer and figure out, do they converge or diverge by the ratio test, or is the ratio test inconclusive? I'll put one over here. Technically, to do the ratio test, we need to take the absolute value. So when you're doing this last expression, when you take the absolute values, the -1 part will go away. So pause your video and use the ratio test on these 3 series. All right, now that you've had a chance to do that, you probably found out the first one diverges, the second one converges, and for the last one, the ratio test is actually inconclusive. For that series on the right there, it actually conditionally converges, but does not absolutely converge. Okay, so the ratio test works because it detects, is a series like a geometric series? So there is another test that does a similar technique, and that's called the root test, which has very similar properties to the ratio test. So the root test tells us something very similar. So we have a series, which is the sum of a sub n, and the a sub n are positive. Well, they don't have to be positive, but because we're going to take an absolute value. And we have 3 conditions. So if the limit of the nth root of the absolute value of a n is equal to a limit L less than 1, then the series converges absolutely. If the limit of the nth root is bigger than 1, then it diverges. And last but not least, if the limit is equal to 1, you can probably guess what happens. The root test is inconclusive. So we can see here the root test. Very similar to before with the ratio test, the root test tells you something about your series if you get a limit that is less than 1 or bigger than 1, but if your limit is equal to 1, it does not tell you anything about the convergence or divergence of the series. So let's take a look at an example. And let's look at the series from 1 to infinity of n to the n over e to the n. So this is our a sub n term, and we take the limit as n goes to infinity of the nth root of n to the n over e to the n. Well, I think we all know what that limit's equal to. If I take the nth root, this becomes n over e, and that limit is infinity, very clearly bigger than 1. And that tells us that our series diverges by the nth root test. All right. So what about the sum 1 over n to the n, where that's our an term? Well, we take the limit again. And again, you can probably do the algebra of what that's equal to inside there. This becomes 1 over n, and that's 0, which is clearly less than 1. And so what this tells us is this sum converges by the root test. All right. Last but not least, let's do a tricky one. Let's go back to our harmonic series, where these are our an terms, and we need to take a limit as n goes to infinity of the nth root of 1 over n, which is the same as the limit as n goes to infinity of 1 over n to the 1 over n. So I'm going to do this limit. So this should be the same as the limit as x goes to infinity of 1 over x to the 1 over x, which is the same as the limit as x goes to infinity of x to the minus 1 over x. So the technique for this is we set it equal to L, and we take the natural log of both sides. So take natural log of both sides, and so what we should get is the natural log of L is the limit as x goes to infinity of the natural log of x to the negative 1 over x, which is the limit as x goes to infinity of negative 1 over x times the natural log of x. And we can rewrite that as the limit as x goes to infinity of negative natural log of x over x. Well, we see that the numerator is going to infinity and the denominator is going to infinity, and so we can use L'Hopital's rule to obtain, this is the limit as x goes to infinity of minus 1 over x over 1, and clearly that limit is 0. And so this tells us that the natural log of our limit is 0, and that means that our limit is e to the 0, which is 1. So after all that work, it told us that the root test is inconclusive. Well, that was a lot of work for nothing, but the point is that when I look back at my original expression, I see that I was taking the nth root of 1 over n. Right here, I was taking the nth root of 1 over n, and whenever you see things like this, the root test is probably not the way to go. All right, if you have any questions, let me know. Otherwise, I will see you all tomorrow. Take care.